So my topic and with Dr. Liu, our topic is discovering and investigating propagated vulnerabilities from Ethereum to its Layer-2 blockchains. So maybe going to the main content, let me introduce myself a little bit. So I have been working on vulnerability research for more than 10 years. So mostly in the beginning years, I was mostly working on mobile security. And at that time, I discovered so many CVEs. And in, I think, 2012 since, and also 2014. And so my PhD study was also about some developing novel static analysis tools for Android applications. So, and after I graduated, with my students, we are mainly focused on blockchain system because, the mobile system has been get more stable, and while the blockchain system has more research opportunities. And even recently, we are also put so many efforts on large language models and its security. So let's get started. So in case some of you may not have so much background about blockchain, so let me introduce this Ethereum blockchain a little bit. So it is a very successful open source project. So it was initially crowdfunded in 2014, and since then the development has begun, and it has been going through so many years, and the price of ETH is also goes up so larger from its initial ICO price. And also initially Ethereum is only a more advanced version of Bitcoin, so it still uses POW consensus mechanism, same as Bitcoin. And its unique thing is it develops a smart contract platform for the decentralized applications. And so initially, when Ethereum went online, it was still a POW network. However, as you know, from the newspaper, such POW is not environment friendly. So later on in last year, so the Ethereum Foundation has changed the network from POW to POS, the so-called proof of stake. So that means each validator, they need to stake certain amount of ETH, the cryptocurrency of Ethereum, and a user can also delegate their ETH to those different node providers. And so the nodes with more ETH staked will get more ETH interests. So, and then currently the Ethereum network has become more environment friendly. And as of this week, there are already more than 2 billion transactions has been sent on the Ethereum main network. And also, even on the main network alone, there are over 1 million token contracts has been created. So, as you may probably know, the language of smart contracts is called Solidity, and it also appears in the list of top programming languages 2024. So it is get more interest from the general public. And another metric is the so-called how decentralized of our blockchain. As you can see this figure here. Here actually we can see there are over around 5,000 nodes that is currently running for Ethereum. Each node they need to stake certain amounts of ETH. And the most country is still US, because the major cloud providers such as Amazon, Google Cloud, and Microsoft, they are currently the dominant player for such POS systems. So they have so many nodes here. And most the top 10 nodes are mainly from the developer countries. But one thing you can notice here is Iran also has so many nodes, maybe because their native currency is not very stable, so they want to invest in cryptocurrency. And but there are still problems. So as you may probably know, the Ethereum suffers from low throughput and also the expensive transaction fees. So currently Ethereum has only 14 TPS. TPS means the transaction per second. So it is not compared to the Visa and the MasterCard. It is quite slow. And another more serious thing is that the transaction fee was actually quite expensive. So even currently is in the bear market, the transaction fee can be up to $1 per transaction. And as you can see here in the previous bull market, you can see the typical transaction could be a dozen of the US dollar and even $250. And this particular time may be due to the popularity of NFT, the cryptocurrency. So it takes so many transaction fees. And to address this problem, so naturally those blockchain vendors, they propose different layer 2 blockchain networks. So I will introduce their architectures in the next two slides. So basically there are two current mechanisms to develop the layer 2 Ethereum blockchain. One is it is so-called the true layer 2 networks. So these networks, they will bind to the Ethereum mainnet, and so they are, you can think about they are only sort of like side blockchains. But on the other hand, we also have some standalone blockchains such as Binance Smart Chains and Polygon and Avalanche and Phantom. They all use the same EVMs, the Ethereum virtual machine, so that they can be compatible to the existing smart contracts, but they were not connected to the Ethereum, except the Polygon has certain mechanism to connect to the Ethereum. So this is the current state of these the so-called layer 2 blockchains for Ethereum. And actually this because open source is very common in the blockchain world, so these projects, they will actually copy and customize the Ethereum source code. So here it is the main repository of the Ethereum that will be utilized in those layer 2 projects. So here you can see this project is very popular, and it is also very frequently being developed. And actually, last summer we actually did an investigation of these major layer 2 projects. As you can see here, this table list the projects that has very similar code as Ethereum. So such as Binance, Avalanche, Polygon, Celo, and Optimism. And especially, because at this time the market cap of Optimism is still low, so it is only ranked in this place. but now it has been I think in top 100. So especially for the optimism, it's further trigger many blockchain networks, such as you can see here, this the Coinbase network and also Blast and Mantle, they all use the same technology of the Optimism. So even this table only lists Optimism alone, but it actually will affect several other more blockchains. And in terms of the architecture of the typical connection between Ethereum and its layer 2 blockchain network, this figure has given a very good examples. So typically this is the layer 2 network, and this is the layer 1 blockchain networks, such as Ethereum. And instead of from the user's perspective, previously they will direct send the transaction to the Ethereum, but now they will only use layer 2 network to send the transaction, and this sequencer will order these transactions and also run them into the layer 2 network's executor, which is these two parts are mainly very similar to the Ethereum virtual machine. So here then they will further pack this transaction into blocks, and they have standalone. They have two new components. One is the submitter, and this submitter will simply submit the transaction data to the layer 1 blockchain. And on the layer 1 blockchain, there will be some smart contracts written in the layer 1 blockchain, and these smart contracts will receive this transaction data and also send back it to the prover in the layer 2 networks, and this prover will further give some proof to this smart contracts, so that the Ethereum can know that these transactions are actually happened, and they actually happened on the blockchains. So here in this talk we will not cover the actual details of these layer 2 networks. Instead, we will focus more on the code level security in terms of the vulnerabilities of how a vulnerability in Ethereum can affect the vulnerabilities in its layer 2 networks. Okay, so actually then we did some research. So in the past actually two years, we developed a tool called BlockScope, and it is also open source in this week. And it is a novel patch-based clone detection tool for analyzing and detecting propagated vulnerabilities in forked blockchain projects. So while this talk covers mainly on the Ethereum, but actually it can be also used to analyze the layer 2 networks of Bitcoins. You know, this year there are some hot interest in the layer 2 network of Bitcoin. So here our tool will cover both ecosystem. So from this figure we can see its overall architecture. So initially we will have a component called extractor. So it will take an input of security patch, and this patch could be manually prepared. This patch is the past patch of Bitcoin and Ethereum. So you can manually prepare this input, or simply write a caller to prepare so many patches together. And this extractor then will extract some contest information of this patch code. So in the next slides, I will introduce this contest in more detail. So with this contest information, it basically tells you at which kind of location this patch should be used. And based on this patch, because this patch is from the source repository such as Bitcoin or Ethereum, so we will have another components, the so-called searcher components, to leverage this source patch context to search for the context of the candidate code in the target repository, such as Dogecoin or the Optimism of Ethereum. Then with this identified candidate context code, we have another component fetcher to launch to fetch the candidate code from both target repository and also the original contest information from the source repository, such as shown in this figure here. So this is the original patch information, and this is the candidate code from the Dogecoin. And after that, we have the most important components. This comparator, it is a similarity-based tool to compare how this candidate code is similar to the original vulnerable code, or whether it is more similar to the original vulnerable code, or it is more similar to the patch code. Then we can decide whether Dogecoin has already successfully applied the patch or not. So we can decide it is vulnerable or it is already patched. If it is already patched, we further analyze when in which commits it has been applied this patch. So we can conduct a security study. And because this tool is initially developed for academic research, so this tool has been published in NDSS, a top-tier security conference in academia. So there are two unique design of these blockchain networks. So there are although there are so many clone detection tools, the novelty of our tool is that we leverage the code context to locate only the potentially relevant code. And in next slides, I will introduce this novelty in more details. And another novelty is here we use a similarity-based code match. Actually, we develop a new way to calculate the similarity so that it can better handle the type 1, type 2, and type 3 clones. Okay, so let me introduce the first major components of this BlockScope tool. So here you can see two pieces of code. One is the original patch code from the Bitcoin. Here this is deleted lines, and this is added lines. You can see it add some more checks to avoid the blockchain being has some corrupt blocks. So here we define the context as some nearby the code lines. It could be either in this direction or in this direction. So we use both piece of code as the context of this diff code. Then on the right hand side, it is target candidate code from the Dogecoin. You can see here this part of the context is almost very similar to the Bitcoin, but here it's not the upside context not exactly similar. So how our system will analyze this piece of target code given the input of this source code. So we will first locate two kinds of statements from the contents. We call it, this is the start statement of the context, and this is the end statement of this up context. And similarly, for the downside context, we also have the start statement and the end statement. And after that, we will simply identify some most interesting statements. We call it the key statement. So this one is we use line 5 as the key statement, and for this one we use line 3. And also here we identify the function name of these key statements. Then we simply use the graph to find the corresponding key statement in the Dogecoin here. And here you can see both statements could be identified. Then and also here I want to mention this is also a similarity based search. It is not the exact search. So we use some similarity threshold. And after that, in the target piece of source code, we will do the nearby search to recover its original context. So here we will determine the boundary of this SS and the end statement ES. So here it is similarly, we will do the line-wise similarity so that we know this line is corresponding to the line 1 in the source code. And similarly, we know that this return arrow is corresponding to line 10 in the source code, and this if statement is corresponding to the last line of the Bitcoin. And after that, we will do the entire block of similarity comparison. So that means we will check whether these two pieces of code's context are actually similar. So here you can easily notice the down context is very similar, and here it is also very similar because we have already excluded the irrelevant code statements. And after that, because this code context is similar, we can simply use the middle part. This middle part of Dogecoin is only has one code statement, which is more similar to this the red color vulnerable piece of source code. It is less similar to the green color patched source code. So we determine this piece of code of Dogecoin is also vulnerable to the same CVEs. So we can know it is also vulnerable. And another thing, as I just mentioned, during these components, we need to both calculate the similarity of this code context, but also the similarity of this diff code. So the accuracy of calculating the code similarity is very important to us. So here we have some special challenge, that is in the source code, this S source code, it may have different number of statements compared to the target code, which has another number of the statements, such as this is 5 lines, this is 3 lines. So we need to better handle the P not equal to Q issues. So here our approach is simply to locate the most similar statements. For example, as I just said, we can locate this line 1 is more similar to the line 1 in the target code, while this line 3 is the most similar to the line 5 here. So in this way, we can pair this line 1 with this line instead of the original first line of the target code. And another thing is, because here this one is still not the same line as the original source code in Bitcoin. So we assign a particular factor here. We call it a reward factor here. If this reward factor is not in the same line, then this factor will become smaller, so that we can better handle the code ordering issues. And lastly, we can simply add up all the weighted similarities. Weighted means here we will multiply the line-wise similarity with the reward factor. And finally, we add up all the line-wise similarity, and we can obtain the similarity of the whole piece of source code and the target code. And finally, we also normalize it into the range of between 0 and 1. Okay, so here are the two major components of the BlockScope, and you probably know that in academia there are many famous tools developed in the past. So we also compared how unique of this BlockScope is in compared with state-of-the-art tools, such as this debug. It is also open source. It was developed by CMU in 2012. So at that time, it is a generic source code analyzing tool. It is mainly targeted for the Linux kernel. So it is also used the patch information to do the code clone detections. And the basic idea of this re-debug is that it will it will calculate a hash of each line. Then it uses the hash to compare whether two pieces of code are similar. But this kind of technique has one problem, that if in this particular line, someone changes the token name, such as changes the variable name or the function name, then this hash will not work correctly. So by principle, the re-debug cannot effectively detect type 2 clones. And in the recent years, I think this is this body is maybe developed by Korean university. So it also published in a top tier academic security conference. And its major advantage is it will further abstract such variable name and the function name into some common name, so that it can be immune to the type 2 clones. But this tool still has problems that it cannot handle the type 3 clone, because here you can see this line 4 add up new statements, then it will not think this one is fully similar to the original vulnerable code. So in order to handle this problem, there are some recent research that will conduct more program analysis, such as calculate the control flow, data flow, those kind of things, and to incorporate such program analysis into their hash-based similarity comparison. So this is one path, and for this path, they all use hash-based code matching, because hash-based is you just need to calculate the similarity hash. Once this hash is generic and accurate, then you can search for the similarly vulnerable code easily. So eventually their objective is to generate better hash for the code matching of the basic units. but compared to their tools, our tool didn't use the hash-based hash as the basic unit. Instead of, we use the similarity of the entire code blocks so that we can better handle these type 2 and type 3 variants. And so in order to perform in this way, we, as last slide mentioned, we designed a better way to calculate the similarity. And one more good thing of our system is that we are not language dependent. So here they are mainly focused on C and C++ code, but for our tool we can work in any language, such as C and C++ in the in Bitcoin, and Go in the Ethereum, and even to work on the Rust. So it is quite extensible. So you can check out our source code and further do more extension. Okay, so here we. Okay, let me show you some results. So here we actually did an extensive evaluation. So we use these I think 11 or something forked projects of Bitcoin, and also use this number of layer 2 networks of Ethereum. So in the original paper version, we only tested 6 projects from Ethereum, but recently we extended it to this is a patch. So originally we test only 6 patch from each Ethereum, but recently we test around 19 patch from the Ethereum. So here you can see the number is larger. And here for the Bitcoin, we have totally 32 patches. For example, here you can see in the Dogecoin it has 16 vulnerabilities that were not patched, and it also has around 15 vulnerabilities that were already patched. And for the Ethereum projects, the results are still much better than the Bitcoin system. For example, here you can see the Avalanche has only 3 vulnerabilities not patched. And also this is the latest results of the Optimism. Last time when we tested it has 4 out of 6 had a piece of code being vulnerable. So here we can also see this TP means true positive. That means our tool correctly identifies the vulnerabilities. So you can see this TP is much better than the CMU's read debugger tool. And in terms of the false negatives, here we also didn't miss too much vulnerable code. But for the read debug, it has missed quite a lot for the Bitcoin ecosystem. And one more thing is that the BlockScope, because it uses the search-based similarity matching, so here the speed is also quite fast. Even for some very large projects, it can finish this timing. This is the total timing. On average, it only has 3 to 4, more than just over 3 seconds for Bitcoin projects, and just over 2 seconds for each Ethereum projects. And but you can see for the read debug case, once the code line increase from 300K to 600K, then you can see its time will quite double so much. So it almost multiply by 6 times. And so here that means once the source code to be analyzed is very large, the read debug will has takes more time here. And here we also break down our analysis of the results. Here you can see for the Bitcoin and Ethereum case, most of those vulnerabilities come from the type 1 or type 3. That means they either only deleted some comments or deleted some black lines, or they will add up their own logic. So they typically didn't change the variable name or the function name, but they may potentially add up some new piece of code. And here we can see for each 3 category of different code clone, BlockScope has quite excellent accuracy. And for type 1, it has 100% accuracy because it is almost the same. And for the type 3, it's also much better than the debug tool. Okay, so here we can actually dive in more depths on the root cause why those vulnerabilities could be propagated from the original Bitcoin and Ethereum to their forked projects. So here we analyze all those vulnerabilities and identify the 2 kinds of root cause. So one simple root cause is that because such as Dogecoin is forked from from Bitcoin, and also Optimism is mostly forked from Ethereum. So when they do the forks, the vulnerability is already being propagated from the layer 1 network to the layer 2 networks. So here the red circle means this is a vulnerable commits. Then you see this commits is already propagated into the layer 2 network, but the patch is only released later after the fork. But this layer 2 network didn't timely fetch the patch commits. So this is the one case. And another category is that initially during when this project is being forked, at that time the vulnerability still didn't happen. But later on, when the Bitcoin keep updating its source code, then sometimes one commit might be vulnerable. And at this time, the Dogecoin also fetch these vulnerable commits because the developers didn't know this commit is vulnerable because the CVE has not been reported. And at a later timing, then the Bitcoin developers, they found this commit is vulnerable. So they patch this vulnerable code at this green circle. However, the Dogecoin developers, they didn't timely fetch these patch commits. So in this case, they cause this number of propagated vulnerabilities. And also there is another categories. In this category, it is more complicated. So there are around 44 cases belong to this category. So we call it the mixed type. That means the vulnerable commits doesn't appear in just one commit. It could appear in multiple commits. But the patch commits didn't timely fetched to the layer 2 network. And just now this is about the investigation of why those vulnerabilities could be propagated from layer 1 blockchains to layer 2 blockchains. And regarding the limitation of our tool, there are still some inaccurate case. So there could be a certain type of false positive. So in one case, that is the reason is due to at these vulnerable commits, the Dogecoin developers actually didn't fetch these vulnerable commits, then it will certainly not introduce the vulnerability to the Dogecoin. But we use these patch commits to do the search, then it calls the false positive. And for another category of false positive, that is the patch is already outdated. So then if we use the latest the previous patch, then it cannot accurately identify the vulnerabilities. And also besides the false negatives, the tool also has a few false negatives. That means it miss some vulnerabilities. So in this case, mainly due to the Git commits is quite complicated. So it makes several the patch commits and the latest commits. So we cannot handle clearly which commits is the true patch commits. Okay, that's about the limitation of the tool. And besides this vulnerability detection, we also report actively of those vulnerabilities to the blockchain vendors. In the paper, we reported a total of 110 vulnerabilities to different developing team. And here we totally received 74 positive response. And the Dogecoin even assign a new CVE for its case, and also the Raven coin. And we also received one bug bounty from the Binance case. So this is the good case situation. And for in particular, these highlighted blockchain vendors, they are quite active to our vulnerability reports, especially the Dogecoin. They are quite actively to already fixed their vulnerabilities shortly after we report the vulnerabilities. And but there are still some cases not very good, such as Bitcoin Cash and Digibyte and Optimism from the Ethereum ecosystem. They even we remind them several times, they simply ignore our reports. And I guess there are 3 vulnerabilities still appear in the Optimism. So here, lastly, I will go through some vulnerability discovery in the Ethereum ecosystem. So mainly we cover the case for the Binance Smart Chain and also the Optimism ecosystem. So these 3 chains are all utilize the Optimism technology. So for Binance, we reported 1 vulnerabilities and I think 4 vulnerabilities for Optimism and 5 cases for the Coinbase and Mantle. So this is one screenshot we reported to those vendors in the bug bounty platforms. And so let's first go through this particular CVE case for Binance. Maybe I can first take a look at this title of this report. You can see that the blockchain is still quite different from the traditional software. That in the traditional client software, if it is simply denial of service vulnerability, then it doesn't matter a lot. So, but in blockchain, the blockchain need to be available every time. So those nodes cannot get shut down. So even the denial of service vulnerability could cause true vulnerabilities to those vendors. And this is one category. We can see this case, and this case are all belong to the denial of service. And there are 2 more serious ones that will cause the chain hard forks, such as chain slipped. So this is mainly due to the consensus flaws in the node and even the memory corruptions. So these two categories are the most common vulnerabilities types in blockchain system. And for the Binance case, so it's almost 2 years ago. So we reported this vulnerability to them, and the details is like this. So suppose there is a node that contains the validation node contains the vulnerable piece of code. Then if this node is configured to use the logging mechanism, then it can be made to crash when it received a specially crafted P2P message. And this P2P message is sent from an attacker code. And once the victim code receives this special P2P message, then it can crash. Then if so many nodes being crashed, then the whole blockchain network cannot run anymore. So this will cause the denial of service issue. And the problem of this vulnerability is actually still similar to the traditional the integer overflow. So here the root cause is due to at this particular line of this particular file, it only use the uint, but the patch case is you can change it to uint h, and also you need to change the structure of this particular type. Then you can simply fix this vulnerability. And one more thing, for the Optimism case here, I did a case study in this Go Ethereum platform. Then here we have two transactions. So once these two transactions are launched, then the Optimism can cause some consensus flaws, which will eventually lead to the chain split. So the root cause of this vulnerability is like in this particular algorithm.go files, it still has a type issue that instead of using the uint32, it should use uint 64 so that it can handle these particular vulnerabilities. And similarly for the Coinbase case, it also has a denial of service vulnerability. And here we can see because here it is the Python code, the Ethereum is Go Ethereum is it is not Python, it is written in the Go language. So the Go language has the so-called panic issues. So once these panic issues happens, then it will also cause some crash. Then eventually it led to the denial of service issues. So the simple root cause of this case is this variable, this structure could be potentially being the near, then it will cause a panic issue in the Coinbase blockchain. And lastly, for the Mantle blockchain, it actually has a memory corruption issues, and but instead of causing the denial of service, this time this memory corruption will cause the consensus error here. So we also submitted to the Mantle, but similar to other Optimism projects, they are not very active to such reports. Even this one is very critical because it does not simply cause a denial of service. Instead, it causes consensus error here. Okay, maybe my time is up. So Lastly, I want to acknowledge my former students. They together contribute the development of this BlockScope tool, and you may find this tool source code at this link. And for the white paper, you can use this particular link for the more details of our project. And so lastly, to summarize, we have 3 takeaways. One is we introduce our recent efforts to discover how Ethereum, actually also the Bitcoin, how those 2 major blockchain CVE vulnerabilities could be propagated from Ethereum and blockchain to their layer 2 networks. And in order to help us automatically discover those vulnerabilities, so we develop a novel tool which is in one sentence, it is just to use search-based patch versus code similarity analysis to discover so many propagated vulnerabilities in top blockchains. And lastly, we also analyze some vulnerabilities in the Ethereum ecosystem. Okay, that's all for my talk. So if you have any question, you can ask now.
Do we have any questions from the audience? All right then. Thank you very much. Please give him a big round of applause.
Thank you.